today we'll be doing the concept of limit.
At an initial stage of teaching limit concept, most teachers start with some geometric construction involving an infinite process or an example of a sequence of numbers approaching a value on the number line. So, all the mental pictures and associated processes that students carry along from early experiences are insufficient to remove all their doubts about limit concept.
Ma'am, in school we were taught how to calculate limits, and we were told the steps and the step-by-step procedure. But we never actually understood why we are doing the entire process and what it's going to be used for and why the whole concept is there.
The concept of limit, though not difficult to learn, is a difficult task to teach, especially so when epsilon delta approach is used by the teacher.
A basic problem with the epsilon delta definition of limit is that it can solve mathematical difficulties of a student, but not psychological ones. For example, while teaching limit of a function, a teacher finds it convenient to make students watch the function values approaching a fixed value when variable is taking values very near to some number. But are they really feeling motivated to understand the concept?
Ma'am, you just told us about infinite processes through limits. It's tending to, through infinite stages, it's tending to a certain point, certain limit. Still, I don't have enough geometrical motivations to really appreciate the limit concept. Why are we doing it? What is the geometrical interpretation of it?
Now, at this stage, it is natural to think of a time when no epsilon delta definition was in existence. This reminds us about the work of mathematicians who used geometric approach instead to deal with limiting process. Let us have a glance through history and unearth the past.
Mathematics. Is it like playing a violin? The more you do, the better you get? Or is it like flying a kite? Sometimes the wind is there, sometimes it is not. Or is it like an unread book? You don't know what you're getting into. Or is it like climbing a mountain? You need to take one step at a time if you want to reach the top. There may be 1,000 versions of defining mathematics. But if you ask anyone to give a definition of mathematics, most likely one would tell you that it is a science of numbers and magnitudes. But it is not so. Mathematics is far more than counting and measuring. Darwin, in The Descent of Man of 1871, noted that certain higher animals possess abilities such as memory and imagination. And today, it is even clearer that the abilities to distinguish number, size, order, and form are not exclusively the property of mankind. Experiments with certain birds have shown that they are capable to distinguish between various shapes,
Why?
recognize colors,
Tell me the colors?
Hello.
Good boy.
and count numbers up to 4.
Good parrot. 4 wood.
It appears these primitive notions may have been in use by mankind to facilitate the sense of contrast, that is, for making difference between one and many. For the inequality in size of a wolf and a whale. For the unlikeness of a roundness of the moon and the straightness of tree and so on. Gradually, they must have arisen the realization that there is some sort of sameness From this awareness of similarities in numbers and form, both science and mathematics must have born. But as we know, the beginning of these subjects are older than the art of writing. So, history of any subject depends on interpretations based on few surviving artifacts, on evidences provided by current anthropology, and on a conjectural backward extrapolation from surviving documents. Fortunately, we have other sources of information as well. The origin of the subject can be traced back to the rise of civilizations in the fertile river valleys of China, India, Egypt, and Mesopotamia. And the beginning is attributed to the concepts that deal with numbers, magnitudes, and forms. According to historian Herodotus, agriculture plots along the Nile were taxed according to area. So, when because of annual flooding, a part of plot got swept away and its owner applied for a corresponding reduction in taxes, it was necessary for surveyors to determine how much land has been lost. Obviously, this must have forced the Egyptians to invent some elementary techniques of geometrical measurements. A more direct information about this is provided by Egyptians' Ring the Papyrus, copied in about 1650 BC by a scribe named Amos. This papyrus consists mainly of a list of problems recorded only in terms of numericals and the solutions, purely in a recipe fashion, about 20 of which relate to the areas of field and volumes of granaries. Frankly speaking, the mathematics of Egyptians was fundamentally a tool, crudely shaped to meet practical needs. No theorem or formal proof is known in Egyptian mathematics. Some of the geometric comparisons made in Nile Valley, such as those on perimeters and areas of circles and squares, are among the first exact statements in history concerning curvilinear figures. The Greeks' intuitive understanding led them to assume that the simple curvilinear figures have areas that are geometric magnitudes of the same type as areas of polygonal figures. So, they attempted to determine the area of a curvilinear figure by exhausting, that is, by filling it up with polygons. The basic idea in this method consists of showing that area of a given figure, when filled with inscribed polygon, can be made as small as desired by increasing the number of sides of the polygon. For the first time, the method of exhaustion was put on a scientific basis by Eudoxus. According to him, if from any magnitude there be subtracted a part not less than its half, and once again from the remainder we subtract not less than its half, and if this process of subtraction is continued, ultimately there will remain a magnitude less than any pre-assigned magnitude of the same type.
Let C be a given circle and epsilon be greater than 0. To illustrate Eudoxus' method of exhaustion, we compute the area of circle C by filling it with inscribed polygons. Let's begin with a square EFGH inscribed in the circle C, which we denote by P0. We may write M0 for the difference between the areas of circle C and square P0. Next, we double the number of sides of P0 and obtain a regular octagon P1 inscribed in C. Let's write M1 for the leftover area of circle C which remains unfilled by the polygon P1. So, continuing in this way, we can get a sequence of polygons P0, P1, P2, P3 and so on up to Pn, where Pn is having 2 to the power n plus 2 sides. Here, it is important to observe that as n increases, the perimeter of polygon Pn gets closer in magnitude to the circumference of circle C. In general, for each n greater than or equal to 0, let's set Mn for the leftover area of circle C, which remains unfilled by the polygon Pn. Thus, if we could show that Mn minus Mn plus 1 is greater than half times Mn for all n greater than or equal to 0, then by exhaustion property, it would follow that Mn is less than some arbitrary epsilon for some large value of n. This, in turn, implies that the difference between the areas of circle C and polygon P is less than a pre-assigned magnitude epsilon for some polygon P. Let's consider the case where n is equal to 0. That is, we shall show that m0 minus m1 is greater than half times m0. Here, m0 denotes the area of that portion of the circle C from which the area of the square P0 is removed, and m1 denotes the area of that portion of circle C from which the area of octagon P1 is removed. So, m0 minus m1 will give us the area of that portion of the octagon P1 from which the area of square P0 is removed. Here, we may notice that this remaining area of octagon P1 is 4 times the area of the triangle EKF because of the symmetry. Also, it is clear that the area of the triangle EKF is half the area of the rectangle EF F prime E prime. Again, rectangle EF F prime E prime in turn is greater than the area of the circular segment cut off the circle C by the side EF of the square P0. But as we may see, 4 times the area of circular segment EKF is the same as the area M0. Thus, we can conclude that M0 minus M1 is greater than half of M0. Similarly, we may prove M1 minus M2 is greater than half times M1. M2 minus M3 is greater than half times of M2, and so on. In general, by similar arguments, we can obtain that Mn minus Mn plus 1 is greater than half times Mn. From this result, Greeks concluded by double reductio ad absurdum argument that if C1 and C2 are two circles with radii r1 and r2 respectively, then the area of circle C1 divided by r1 square is the same as the area of C2 divided by r2 square. So, if we write pi for the common value of these two ratios, then we obtain pi r square as a familiar formula for the area of a circle of radius r. However, long before Eudoxus, it was known that the area of a circle is proportional to the square of its radius, and its circumference is proportional to its diameter. But the fact that the proportionality constants, say pi, in these two cases are same was not known.
Archimedes of Syracuse, in his measurement of a circle, provided the first rigorous proof of the fact that the area of a circle is equal to that of a triangle, with base equal to its circumference and height equal to its radius.
Here we may have a geometric proof of Archimedes' result. For this, let's imagine the circle C to be made up of several very small circular rings of decreasing radius. In the first step, let's cut the boundary ring of the circle and make it a straight line, say xy. In this way, we may unwind all rings and pile them up on the line xy in the order of decreasing length, starting from the boundary and ending at the center of the circle, say z. Then, here we may notice that the area of the circle C is the same as the area of the triangle XYZ. Also, we may observe that the base of this triangle is the circumference of the circle C, and height of the triangle XYZ is the radius of the circle C. As we all know that the area of a triangle is half times its base into height, so the result of Archimedes follows.
In yet another breakthrough, Archimedes extended the method of exhaustion to what has been termed as the method of compression. Here, in this method, instead of dealing with inscribed polygons, he employed both inscribed and circumscribed polygons. The area of a geometric figure is then compressed between the areas of inscribed and circumscribed polygons that closely approximate the area of the given figure. As you may have noticed, the method of compression in principle share a lot with modern-day two-sided geometric limiting process. Archimedes in his time employed this technique to a circle and obtained the inequality 3 10 by 71 is less than pi is less than 3 10 by 70 towards an estimation of value for pi. In 3rd century BC, 1900 years before the advent of modern calculus, Archimedes evolved various methods of computing volume and surface area of number of geometric figures like sphere, cone, segment of a paraboloid of revolution, and a segment of hyperboloid of revolution. Using modern notations, his solutions can often be interpreted as computations of definite integrals of polynomials of degree up to 2. However, 3 indispensable ingredients of analysis were completely missing in his work. Firstly, no attempt was made by him to obtain a general computation algorithm for the calculation of area and volumes. So, for every attempted problem, a new computation was undertaken without ever realizing the analogy between proofs. Secondly, there was no recognition of the importance of inverse relationship between area and tangent problem. The Greek view of tangent lines as merely the touching lines was inadequate to provide any hint about the rate of change interpretations of a derivative. Lastly, an explicit introduction to limit concept was completely missing. Of all these, a lack of understanding about limit concept was at the root of many problems. And it was Greek's horror of infinity that prevented the development of a usable theory of limits to replace the ubiquitous double reductio ad absurdum proofs given by them.
Paradoxes given by Zeno of Ila about 450 BC deepen the problem further. One of the paradoxes is Zeno's dichotomy, according to which motion is impossible in the following sense. If a body moves from A to B, then before it reaches B, it passes through the midpoint, say B1 of AB. Now, to move to B1, it must first reach to the midpoint B2 of AB1. Continue this argument to see that the body must move through an infinite number of distances, and so it can't move.
But thanks to medieval scholastic speculations on infinity and continuum, 17th century mathematicians were no longer reluctant to introduce infinitesimal techniques. In fact, the rich amalgam of Archimedean problems, algebraic computational techniques developed meantime, and a free use of intuitive concepts of infinity produced a profusion of powerful, though loosely based, infinitesimal methods for the solution of area and volume problems.
In 1586, Stephen was perhaps first to use infinitesimal techniques in demonstrating that the center of gravity of a triangle lies on its median. In this method, we inscribe a number of parallelograms in a triangle ABC of equal height, whose sides are pairwise parallel to one side and to the median drawn to this side. Since bilaterally symmetrical figures are in equilibrium according to Archimedean principle, so the center of gravity of the inscribed figures will lie on the median. Also, we can inscribe in the triangle an infinite number of such parallelograms, and the greater the number of parallelograms, the smaller will be the difference between the inscribed figure and triangle. Inasmuch as the difference can be made as small as one pleases, the center of gravity of the triangle also lies on the median. Johannes Kepler was among the first who used method of indivisibles. He took area of an ellipse to be made up of infinitely small triangles and regarded a sphere as composed of infinite number of pyramids. This technique helped him in deriving a correct formula for the volume of a sphere. Bonaventura Cavalieri developed these techniques further in his two books and obtained an elaborate theory of area and volume problems. Throughout his mathematics, he used a result still known as Cavalieri theorem. Applying this result, he could obtain a correct formula for the volume of a cone. Finding tangents to curves is a part of what we now call the study of derivatives. Fermat devised an algebraic method for finding the highest and the lowest points on certain curves. Geometrically, Fermat was attempting to show that exactly at the highest and the lowest points along a curve, the straight lines tangent to that curve are flat, that is, have slope 0. Isaac Barrow developed these tangent methods further and probably represents the important work which ultimately proved to be the starting point of Newton's work on the calculus, reported in 2 of his remarkable books. In almost all of his work, Newton calculated what he called fluxions to curves, not quite derivatives, but very close. The process he used for these computations was very similar to Fermat. Newton was the first to have recognized that the limit must be the starting point to tangent, quadrature, and related problems. And as convoluted as his language was, the seed of the modern definition of limit was present in his statements. Unfortunately, for many decades, no one took up these hints that Newton had provided. Jean d'Alembert was the only scientist of the time to explicitly recognize the centrality to calculus of the limit concept. In the first careful and rigorous study of the distinctions between continuous and discontinuous functions, Bolzano looked beyond the intuitive notion of the absence of holes and breaks and found the more fundamental concepts that we express today in terms of limits.